Good morning. Welcome to my talk. I'm going to talk about quantum computing and artificial intelligence. Here is the outline of my talk. Quantum computing promises a huge increase in computing power. There are many algorithms related to AI that can be done in a quantum computer. However, the development of technology now, we don't have a very big size of the machine. Quantum optimization promise a near-term benefit to use the current size of the machine. Next, I will describe evolutionary algorithm. It is a subfield of AI that can be used to solve many AI problems. Especially, I introduce a quantum version of the genetic algorithm, a special kind, which I will be explained later. And I will use this algorithm to solve benchmark program called Travelling Salesman Problem. Let's start with the simplified definition of a quantum computer. Okay, so let's say a quantum computer rely on the special kind of memory we call quantum bit. Okay, in this memory, it store quantum information, and with this special property, this quantum bit can be used to perform massively parallel computing. Therefore, it promises huge speed up. In my talk, I will not mention the technology of building the machine. We'll be more concentrated on the software side and how we program them. I will assume that there is some in the future, some machine that we build today will be large enough to do practical computing. In this machine, instead of writing the script and running on the classic processor, which is a sequential, a quantum computer do manipulation on the quantum state of each qubit. And this qubit can have the property that they entangle. Therefore, the one state can affect the other qubit state. Okay. So we have to imagine that the in terms of programming, we have this qubit built into some kind of technology, and we have some operation that perform on this qubit. Okay, and then when this operation we call quantum circuit, right, affected to the state, and then we what they call apply this circuit in step. So this is a programming step. Okay, and in the end, we measure the state of the qubit, and it collapses down into just one answer. Okay, so the information does not flow anywhere. It stays in the quantum bit, and the operation performed on the quantum bit is a kind of a operation we call program. Okay. The type of operation has been have been agreed upon, and with some very good basis, theoretical basis, that this kind of a quantum gate. This is the lowest level that not dependent on technology. Okay, so we can imagine such a quantum gate as such a kind of machine language for our quantum computer. These gates can be composed to perform some better function. On the left-hand side, the name and the symbol of the gate, and on the right-hand side, the kind of transform function of this gate. This gate can be composed together to perform a high level of function, such as in this picture. Okay. I simplify the view of programming a quantum computer. This is a regard of type of the computer hardware. The next step, I describe the algorithm that perform on quantum computer. Okay, so using these, we're trying to use the quantum computer to solve AI problem. I will concentrate on a narrow subfield we call quantum optimization, which also can be used to solve many problem, real world problem. You know, in a classic optimization, it run on a current computer. Okay, we can solve quite useful, many useful application, right? Most popular family of algorithm for optimization is using the quantum computer. Okay, it's a variational quantum algorithm. It's developed for a wide range of application, and for example, simulating dynamic of a quantum system, right? Which in a way you can use it to perform kind of chemistry, computational chemistry. Okay. Because you can set up the information such a way that it simulate a system of a molecule, and then you can use this algorithm to find the minimum energy at the ground state of solving system of linear equation. Using the quantum computer is just like setting up the what we call system to find the ground state of a wave function, which describe a configuration of system of particle, right? That has a certain energy. Its ground state actually describe the most stable configuration. You can see on the right hand side on this picture, right? It's the quantum circuit or our quantum computer is used in conjunction with the classic computer in hybrid. Okay, right. We set up a quantum circuit to find some initial configuration, and then kind of solving the lowest energy state, right? And then we have to use the initial kind of guessing the variation. I think it's kind of having a good guess of the solution and then improve the parameter to be used for the next guess. So this kind of optimization is done in any classic computer, right? The quantum computer system is using is a kind of simulate the system under investigation itself, in which it is faster than classic. but it's a hybrid, so it's not totally a quantum computer job, right? Some uh, useful algorithm has been invented to be able to that this kind of algorithm can solve combinatorial problem. Which is useful to be used on the current machine, which is have not too many number of qubits. And this is quantum approximation optimization algorithm is invented around 2014, I believe. Right? It uses a quantum computer to generate a good guess of the ground state of a wave function, right? For example, for a chemical system. Right? Because they based on the belief that the quantum computer is can be set up that is a model of the nature itself. Okay, this method prepare the eigenstate and explore quantum estimation. Okay. So you can see it have two step, right? One is preparing initial state, and then mixing, okay, have group we call changing the parameters, so the quantum state will be biased to one or another. Okay? And then the parameter itself is setting in a kind of unitary matrix. Okay. This is successfully used to solve the MACUP problem. Okay. The MACUP problem is a kind of if you have a graph, you can divide the graph into two groups, such that the connection between them is maximized. This kind of variational quantum algorithm is a kind of systematic guess. Okay. It gives a good approximate answer most of the time. In average, it works faster than any known classic algorithm for this particular problem, and it can solve. Setting up this uh, can solve other problems as well in combinatorial optimization. Okay. Another another view of more than just describing that using mathematical equation, you can imagine the kind of flow of this algorithm. Something like this is prepare the quantum state, and then it uses a classic optimizer. It compute the expected expectation or evaluate the energy state. Okay, right. This is done in the quantum circuit, and then we read that out, and then using a classic computer to search or change the parameter that we use to prepare the next quantum state or the go another loop. Okay, so this is using a quantum circuit and a classical circuit to classical computer in hybrid mode. Next, I will talk in a bit of details on my experience on solving optimization using a quantum computer. I'm interested in the evolutionary algorithm. Therefore, I use one special form that can be implemented kind of very efficiently in a quantum computer. I call compact genetic algorithm. And my initial work at show no speed up, and then with some insight, we modify the program, and then later on I can really find some exponential speed up. But however, it is approximate, right? Rather than, well, you cannot say approximate. Evolution, you really kind of exploring. Okay. Why evolution algorithm? I find that it can be applied in many applications, right? Which, of course, evolution algorithm is a type of AI, right? And it can use more than just solving numerical problem. It can solve the kind of design problem. Okay, you can use it to find the shape of the best heat flow for heat uh, transfer. Okay, I have done that in the past. And the simplest kind of evolution algorithm is a genetic algorithm, which represent the parameter, I call it solution by binary bit string. And special kind of these compact genetic algorithm, which have a similar computational power, is called compact genetic algorithm, in which rather than storing each individual solution, we call the probability density function, okay, into a kind of probability vector, okay, in which we can sample the solution from that space. We call compact genetic algorithm. All these are classic algorithm run on classic machine. Okay, so let me explain quickly. Oh, okay, right. What the compact genetic algorithm different from simple genetic algorithm is we have a initial probability vector, right? Maybe we start with the all of solution is possible, okay, and then we from this we sampling to candidate, okay, let's say called A and B, and then we evaluate the goodness of these two candidates, and then we bias or update that probability vector toward the better one, and then the repeat. Okay, so we don't have to store individual. All solution is in the probability vector. Okay, for the normal, I use some example to use this compact genetic algorithm to solve using quantum computer. The problem in this particular is well, this is you can set up the evolution algorithm to solve problem. You have to find the right representation and the objective function that appropriate for your problem. Okay, so a normal one, this is a straight kind of simple-minded implementation of this algorithm on quantum computer. We set up quantum bit, okay, and then quantum bit as directly corresponding to a probability vector, okay, and then we sample to individual from this quantum bit, okay, and then we evaluate the goodness and select the better one, and then we update or bias to the next step of a probability vector toward the more likely to generate the winner, okay? And then we repeat this step. Okay, so this is just a classic algorithm running on quantum computer. So therefore, it's almost exactly the same performance, so to speak. Okay, so how we can get the quantum the speed up? Okay, I modify a little bit after I gain some insight in its behavior of this kind of program. The it is the third step, the blue one, that the second generation, rather than sampling, we can, with some kind of condition, we can generate the second with the one that is better than the first one. Yeah, so this is a crucial one, right? And the rate is the same. Just this modification, or which can be done on a quantum circuit. It help the whole algorithm to speed up. Okay, this is to show the very old result from 2012, I think. the setup for this problem, this is running on some quantum computer simulator, very early days. Right? It solved some problem of that we call in evolution algorithm a trap function, which there's if you you're trying to find but by descending to the slope to get a better solution, you get to the wrong peak, and then finally let's say we bias toward all the bit become if the solution is all the bit become 1, I try to get all the fitness of the bit 0, right? The more bit 0, you have better fitness. But however, the best one is flipping. Okay, this is a kind of defeated all the transient descent. Okay. So you can see it is a hard problem in terms of evolution. In this experiment, we use 6 qubits available at that time. Okay, in the simulator, which is the limit. If we can reading out, because it is simulator, the state of 6 qubits, you can see that it is right. It's when the time goes on, the probability of getting some solution change, right? Right? Change, and finally select the right one. Okay. So this is a kind of a rough behavior that you can expect from quantum computing. Yeah. All right. The next step is we use a more of a modern version to solve more of a well-known problem on combinatorial optimization. Okay, so this is an algorithm of the compact genetic algorithm, classic one. This one a bit of modification of keeping the best candidate so far. Okay, and this keep it from falling in, improving the conversion a lot. And this one is a quantum version, and in generating the second candidate, we use a Grover function it's a quantum circuit function. Okay. I'm not going to explore too much detail because of the time limit. So that's the only difference on generating the another solution. Right? And to use it on a quantum computer, we also map the problem of GSP into Ising model, okay, a kind of particle in which it have only state up or down. Okay, so it's a binary state. Okay, let's talk about concrete example. We demonstrate a small size TSP, right? You can see the maximum 4. Now I can do a 5 city, which is trivial. The connection is rather simple weight or integer 1, 2, 3. Okay, this is because of the limit of the size of the machine that we try. Even in the simulator, if you have a large enough size, it will run forever. We use a part representation to represent a feasible tour as a permutation of the city. I think, right? So it's a kind of, if you have 4 cities, 1, 2, 3, 4, 1, 3, 1, 4, that sort of thing. And total of number of feasible edge is a set of binary string. And we map it using this kind of matrix. The one is the city, and the other axis is the step. Okay, right? You can do both ways, right? And so you have to map this into Ising model so that the problem of n city become n square spin. Okay, required to solve to represent this problem. In this example, at step 1, we we select city 1, and step 2 we select city 2, step 3 we select city 3. Therefore, this set, this matrix represent the root 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. Okay. We also have to implement a kind of we call manipulating the quantum step, right? So this is how we write it in objective function, right? It's the cost function is a total distance and the constraint of checking the feasible part. Okay. When we change it into quantum circuit, okay, it looks like this. On the left hand is a kind of the preparing the quantum state based on the probability, right? Encoding. This is a kind of four qubit word. Okay, the one that we solve it need about 10, 12, and then this is a kind of adjusting the parameter called tweaking the state. Okay, because this fuses circuit, and then to generate the or to check the to what I call to get the valid candidate, we must use this circuit, right, to check the feasible solution. Okay. This is for this circuit show you just for 3 cities. Okay. And there's some what I call the running time result. Okay, and the x-axis is the size of the kind of the pool of candidate, or how many candidates we have to sample. Okay, and the vertical is the achieve the accuracy. Okay. So this is kind of experiment and show you the number of iteration on generating the second candidate. We change the Grover iteration and the number of repeating the run. Okay. Of course, the real in real running time is not faster than solving this problem in classic. Okay, especially this TSP problem is well known in classic, and solving this state-of-the-art algorithm is very fast. Maybe we can solve 1,000 cities very realistically. So why quantum computer? It is not really run that fast. Okay, but it is possible, right? I think it's studying a quantum computer. It writes to the new way of thinking, okay, new algorithm, new approach. Right? It's it also because we haven't done very well on today computer machine. Okay, but if we think differently, we can really solve really difficult problem, because we can promise a huge speed up. Okay, maybe many. Well, we can solve. We believe that the new way can solve the problem that classic computer cannot solve. Okay, I have yet to demonstrate clearly. Okay, and I have high confidence that this current state of development of technology will be resulted in practical machine that can be used for the realistic problem. Right now, it's too small. Okay, and this knowledge, this experience will change the way we develop the computer further. Okay. Give you some reference to one of my very old work, and one is a more current one. Okay, and if you want more information, you can search my webpage and get the paper and more details. And I'm happy to answer all of your questions. Thanks.